Let's recap some definitions of set operations. So if we have a set A, which is a subset of a larger set omega, then we wrote A with a superscript C like this to mean omega set minus A. And you'll remember that that was defined to be the set of all things in omega which were not in A. And to connect this with some of the logic we've been doing, we could rewrite that as saying x in omega, the set of all x in omega, such that it's not the case that x is in A. So introducing logical notation like this is going to allow us to use some of the logical equivalences we learned to prove identities connecting sets with one another. And the identities we're going to be interested in are the counterparts of De Morgan's laws in logic. So here are De Morgan's laws for sets. We take sets A and B, which are subsets of some larger set omega, and we let A with a superscript C and B superscript C be the complement with respect to omega. So what that means is A complement is the thing that I defined on the introductory slide. It is omega set difference A, and B complement is omega set difference B, the set of all things which are in omega and which are not in B. So what we then need to do is to prove the following two results. So the first one says that the complement of A union B is equal to the intersection of A complement and B complement, and the second one says the complement of A intersection B is equal to the union of A complement and B complement. So how do we do this? Well, we just use some logical equivalences which we've proved before. Specifically, of course, we use De Morgan's laws in logic. So let's write out the definitions. I'll do part one of this theorem. So if we write out the definitions, A union B complement is equal to all the things in omega which are not in A union B. Okay, what's the definition of being in A union B? The definition of A union B is that something is an element of A union B if it's an element of A or it's an element of B. So we can rewrite this as x in A or x in B. And now we have a logical formula. We have the negation of an or statement. So we can now use De Morgan's laws from logic. And that would tell us that this is all the things in omega such that x is not in A and x is not in B. So this is by De Morgan's laws in logic. Okay, what do I have here? I have an AND statement. So by the definition of intersection, this is the intersection of all the things in omega such that it's not the case that x is in A and set of all things in omega such that it's not the case that x is in B. So this is just using the definition of intersection. Remember that we defined, let's say x intersect y was defined to be all things of the form, let's say A in x and A in y. Okay, so where are we? We can now just re-express these two sets. We've got the set of all things in omega which are not in A. It's precisely, by definition, A complement. And similarly, the second set you've got there is B complement. So we've now proved the first of De Morgan's laws, and the second of De Morgan's laws could be proved in exactly the same way using the logical equivalence, the other logical equivalents from De Morgan's laws in logic. Okay, so let's now just generalize this a little bit, just as we generalized De Morgan's laws in logic to more than one well-formed formula. We can do the same for more than two well-formed formulas. We can do the same for more than two sets. So more generally, if you have A1, A2, and so on are subsets of, so that all subsets of a set omega. Then the two generalizations are that, first of all, if you look at A1 union A2 and so on, and then you take the complement of this, then that's the same as the complement of A1, intersect the complement of A2, intersect, and so on. And then the other, De Morgan's law, is for intersections. If you take the intersection of A1 and A2 and so on as many times as you like, even infinitely many times, and you take the complement of that, then the result is the union of A1 complement and A2 complement, and so on. Okay, so before I end this video, I want to think about one maybe slightly surprising aspect of the way we've stated these results, which is that we had in these results a set omega, a kind of universe omega, to which of which all of our sets were subsets. And you might ask, why do we need this omega? Right, so what will be wrong in taking a kind of absolute complement, where you don't just think of all the things in omega that are not in A, but instead you think of just all the things which are not in a set A? So isn't this okay? Well, the answer is no, that thing is not okay. And the reasons are for when you use this kind of what's called unrestricted comprehension, you can cause problems in this kind of informal set theory. You can end up with paradoxes in set theory, contradictions. And this kind of problem is the reason that formal set theory was developed. So you don't need to know about any of this stuff in Math 5, or simply be careful to avoid any constructions which led to a contradiction. If you would like to know some more about this, then you can search the internet for Russell's paradox, or you can look in the further reading section of chapter 2 of the notes for Math 5.